Well, I was a small boy in the 1950s in the United States, and at that time there was a strong effort to encourage people to do science and engineering. That was the so-called Sputnik generation, in response to the Russian satellites that were launched before the American ones. And so I was always interested in science, and my father certainly encouraged me to do that. He was an insurance not a salesman, but he ran an office of insurance. And so I can't remember a time when I was not interested in science and engineering. There certainly were teachers that encouraged me in one way or another. I had a very good chemistry teacher in high school, and if I'd had a very good physics teacher, I might have gone that way, but this is the way almost every scientist tells a story of some story like this where, a chance occurrence had a big influence on their career. Certainly I had good undergraduate teachers at Rice in science. Yes, well, it was my father felt that everybody should work. It was not good to have free time. It's very different than the experience now for high school students in the United States. And he went actually out and got me this job with the man next door who owned the hardware store. And I was a clerk making 65 cents an hour. That was my salary. And but it was very good because at school I was more theoretically inclined, and I didn't have much experience with mechanical things. For example, I didn't take cars apart and put them back together again. And so this time in the hardware store was quite good on learning about tools, but also learning about people. Everybody comes into the hardware store. You have to deal with the customers. It's any kind of sales job. And so that was good. I worked, basically, it's hard to imagine. I worked, let's see if I get this straight, 24 hours a week. Either 2 or 3 hours after school on every school day, and then 8 hours on Saturday, and then 2 hours on Sunday. It's a lot of working. There was not much time for anything else. It's amazing, that I could work half time, and still do well in high school, yeah. Well, my time in the Navy was quite important to me. It helped open my eyes to the real world. Not many scientists in the U.S. have any experience out of universities. They've been in the university their entire life. But I was 19, I think, and I finished my freshman year in Rice, studying physics, chemistry, math, and then went off in the summer to train with the U.S. Navy in the fleet, and in an old destroyer out of San Diego. And all those experiences were extremely vivid in the real Navy. I learned about electromechanical computers. They during World War II, they didn't have digital computers. There was no software, but they had machines where this mathematical function was encoded in the shapes of cams. And these were hardwired computers to solve one problem. The problem was how to aim the guns on the destroyer. And so this kind of experience, I went on an aircraft carrier one summer in the Mediterranean. I found out later the aircraft carrier was carrying many nuclear weapons, preparing for war with the Soviet Union. And anyway, they said these summer training cruises had a big effect on me. When I actually went on, I went on to get my PhD, and then began to serve on active duty in the Navy. But I was lucky to I was assigned to the Naval Research Lab, which is in suburban D.C., and I was able to do more or less basic research there for the 4 years that I was on active duty, and I got to learn a lot of things outside of academic chemistry. Just the kinds of technical issues which are important in a mostly engineering laboratory. So all of that was good. In those days, there was a draft in the U.S., and so I was expecting to go into the service in any event, and my father had been in the Navy in World War II, and so that predisposed me, and I went actually to Rice on Navy scholarship. That was part of it. I never expected to be a scientist. I thought I would be a businessman like my father, and I thought I would serve in the military before getting serious about business. And that's how I was thinking about all of this in high school. Well, it was my experience, undergraduate experience. I became more and more interested in science, and in particular, I was interested in quantum mechanics. I remember my reasoning as a senior. I was thinking, quantum mechanics is so interesting, I'd like to study it some more just to learn more about it, even though I'm going to go off and be a businessman and not really use it. And I was lucky that the opportunity came to, the Navy gave me first a leave of absence to go to grad school, and then the Navy assigned me to work in the laboratory research at the Naval Research Lab, and all of that contributed to my career, made it possible to be a scientist. Well, it's the old-fashioned way of doing science. I like to understand how and why things work. And I don't really love machines. There are some experimentalists who really like to build machines, and they're not particularly interested in the problem that they solve with the machines, to measure something. I'm just the reverse. We build machines in order to solve a problem that I'm really interested in, basically. Well, I didn't teach for a long time because, I went to Bell Labs. That's a industrial private enterprise. I mean, it's not the school. There are no students there. So I did not teach, but I was certainly missing teaching. I'm missing being around younger students, and that's one of the reasons I came back to Columbia. And I enjoyed teaching freshman chemistry at Columbia for many years. There are a lot of smart students at the undergraduate level at Columbia, and very few of them are going to become professional chemists or scientists. They all go off into med school or lawyers and all these things that people do, go into business in New York City. But I'm teaching them the principles of physical science, probably the last time they'll see them in their major, And I enjoy that because the U.S. does not need more PhD scientists. What it needs is every citizen to be somewhat scientifically literate so that decisions can be made, so that science is not black magic. For many people, it's just completely black magic, and that's not good for society. I think many people have the experience that it's a fun and a delight to have a student of high scientific ability, that's not hard to teach and picks up very quickly. And certainly that was my relationship with Wendy and with the previous postdoc in that program, which was Paul Olivasatos. And Wendy had started off graduate school as a theorist. And yet when he came to work with us, he was doing experimental work, mostly synthesis, and this was, he didn't know anything about it, but he had great enthusiasm and he was highly intelligent, so picked up pretty quickly, and he had other people to mentor him around Bell Labs as well. The strength of Bell Labs was that there was always an expert nearby that you could talk to. So if there was a field I didn't know anything about, or that Munji didn't know anything about, we'd try to find a guy in the building who was an expert in that area, or at least knew more about it than we did, and then go and ask us his advice. And the culture was such that he was obligated to talk to us, not obligated to work on our problem, to abandon his own research, but to advise us. So it's a very quick way to learn. And you could turn on a dime. Essentially, if you found a better problem, you could quickly switch your own research into this better problem without any prior obligations to the previous work. So it was great delight. It was great fun to work with Munji, that's for sure. Well, I mean, a lot of times in research, perseverance is important. Very often your initial ideas are wrong, and you try to do something, it doesn't work, and then you have to reconsider. You may start an experiment thinking that you're going to show one thing, and it doesn't come out that way. It points in another direction. You have to sit down and rethink. And I think there are very few accidental discoveries which are immediately important to the entire scientific community. You look at, someone told me this morning that the average time delay between a discovery in chemistry and a Nobel Prize for that discovery is 30 years. And that shows that it wasn't considered revolutionary when it was first made. People were still struggling with it to figure out, is this good for anything? And it only becomes apparent over time that it has a real value. I mean, any new result, any really unexpected result takes time to sink into people's minds, so that they can think it through the consequences of it. Most of science is not really conducted on this eureka principle, that I'm Albert Einstein, I sit down and I think through this and I come up with a great theory which changes the world. That almost never happens. Has not happened since the early days of quantum mechanics in world science. I mean, it happens. Structure of DNA was a case where they were able to. They were at the right place at the right time, and worked hard on this structure and fell into it. Sort of, the initial ideas failed, but and they had help from the real chemists, in Cambridge, and so there are a few things like that, but not many. Well, so when I was in Bell Labs, collaboration was the basis of almost everything. You had a certain expertise in your own laboratory. I was a laser spectroscopist. I could do laser spectroscopy on many different samples. But to work on a given problem, you needed people of different you needed people who do electron microscopy of the sample, and people who understood separation science in analytical chemistry. And so you could talk to them, and they would agree to collaborate with you because they thought it was an important problem, and they could make a contribution that you could not make. It's not necessarily true in academic life. In fact, there are many schools that pride themselves on the fact that they don't really have strong collaboration among the faculty. Each faculty has its own self-contained universe, basically. But I always like collaboration better because, to make progress, you have to deal with the weakest parts of the experiment, So we have to work on the weakest parts of the experiment, even if nothing in our background qualifies ourselves to do that. So, and at Columbia, we tried to institute a similar system to what we had in Bell Labs and what existed at IBM before. A much more collaborative effort among the junior faculty who were part of the material science effort. And the science is going in that direction. Basically, that my whole life, the institutions in the U.S. have stressed interdisciplinary collaboration. People from different backgrounds forming a team to work on a specific problem and to get money from the federal government to work on that problem because they are a team. In industry will always form if there's a problem in industry, it works the same way. They'll form a team with, if there's something wrong with the manufacturing or they're trying to make an improvement to the manufacturing, they'll form a team of maybe 8 or 10 people that have wildly different backgrounds, scientifically, so that each person might see the problem from a different perspective and can contribute to the overall success or failure of the team, to solve that problem. Well, this was the height of the Cold War, and the Russians were our enemy. And we tried to keep contact with the Soviet research effort, basic research effort, but it was hard. Yekimov was not allowed to travel to the West to talk about his research. His research was published in Russian, not English, and in obscure journals, and in the beginning, I asked around a lot of people what kind of research had been done on small particles, or nobody knew of any research, it was all zero. So that's the situation, I finally I found Yekimov's paper after a couple of years. I found his paper in translation in the American Physical Society, I guess, or American Institute of Physics used to do translations of some of the Russian journals, and I found an abstract. I don't think it was the entire paper, it was just the abstract, that was translated into English. That was a surprise. And then I wrote to them in the Soviet Union, just in surface mail, without any, there was no email in those days. I just a handwritten letter to one of Yekimov's collaborators, Sasha Efros. And I think I sent them a preprint of my work along with his handwritten letter. This was, as I say, in the depth, at the depth of the Cold War. Yes, for sure. You still have to have centers which are experts at doing specific things, like understanding the human genome and things like that. But taking the tools, I mean, those centers will much more open now about adapting tools from other areas that may give some progress on understanding the human genome. Yeah, it's certainly a big advance over what it was when I was a small boy and when I was a young student. It's mostly having to do with the choice of the problem. You have to make it. You have to choose what to work on. If you're doing basic research, then you have to start off on one problem, and you don't work on all the other possibilities. And you don't know in the beginning what the heck is going to work out better than anything else. And so it's always have an open mind for and a broad interpretation of what your goal is. In engineering, what people prize is the ability to make something cheap enough, which works well enough that people will buy it. You don't have to be first, but you have to have a product which works well and is cheap, relatively cheap, okay? But science is different. Science values very much the people who first think through the issues in a field which is completely unknown to the rest of the scientific community. And if you start experimental work on something and maybe 5 years before anyone else picks up on it and realizes it's actually important, All kinds of examples in Nobel Prizes of people who invented effectively a new field that was not really, their colleagues didn't understand why they were working on it because it was so different than the experience, the cultural situation in their community. Therefore, they had 5 years to work on it or so, and work out the basic ideas without competition, so to speak, or at least, what science prizes is new ideas, and I guess the measure of a new idea is it actually affects the work of other scientists somehow. Either intellectually it affects the work, or they shift their fields in response to some paper that you published, or you invented a technique or a machine that could be useful in their work, even though that was not what you did. You just invented the machine. They decided how to use it for a really good problem. But anyway, they had all these different ways. You influence their work. You influence the work of the community, and so that's what science prizes. It goes forward because of these individual contributions. in your own research, you have constant failure. Basically, it's rare that something works out well. And you have to sit back and reconsider and find a different way to do the same thing. So in that sense, failure occurs all the time. Drug industry, the huge amount of money spent in the drug industry on research and development, and almost none of it actually leads to new drugs because we just don't understand the principles, what's going on inside the body. You may have some idea about how this drug will interact with certain proteins, but the body is so complex that only God knows how it's going to work once you put the drug in there. Things like that you can consider failures, I guess. If you find trouble with somebody else's work, most scientists will step around it, basically, not really devote their own time to confront the other person unless it's really a super critical issue or something like that, because you'd much rather work on your own ideas and to make them, you'd much rather spend the available time and mental energy working on your own ideas than spending your time and mental energy to disprove what others have done is wrong, which it may be wrong. Anything really important will be picked up pretty quickly and reproduced in the lab. And so many scientists will wait until something has been reproduced somewhere else in the world before they get serious about thinking about what this first paper has said, because there's only so many hours in a day. You have to somehow maximize your chances, that you'll do something important. Well, I had a very good history teacher in my first year at Rice, and he opened up my ideas about history. History is really interesting, study of the people who have changed the world, and so I began at that point to study history, mostly American history, and I became interested in investing at one point. My father left me a little bit of money, and so I never spent any time thinking about that. But then I figured I should spend a little time trying to understand this investing so that we don't make huge mistakes, and I do enjoy gardening. My mother and my grandmother and my maternal grandmother were very strong gardeners, and I very much liked that. I wish I would have done more with that over time. If we lived in a house that had more sunshine, I would have been a better gardener,